So we will continue with a set of talks from the submissions. First, I would like to introduce Andreas Bergmeister. He's a doctoral student at TU Munich and MCML, advised by Stefanie Jegelka. He holds a bachelor's and master's degree in computer science from ETH Zurich, and today he's presenting his recent work on scaling diffusion model training with reinforcement learning. Stage is yours.
Hi, everyone. So I guess I can just continue where we left, so diffusion and flow matching models. So if we think about the breakthroughs of artificial intelligence in the last decade, like everything that got people excited, it was really always an instance of generative modeling. Text generation, then image generation, video generation, and protein folding. These days, robotic actions. And apart from text generation, text is quite simple, right? Text is just a sequence of discrete tokens. But if we move to something a bit more complex, then the method that is used to generate all of these representations is our diffusion models. Now, why is that? So in generative modeling, the goal is that we have some target distribution, and then we want to learn a model that generates samples from the distribution. Now, we could ask the question of how does this distribution look like? But in a high-dimensional continuous space, this is a very difficult question. So the ingenious idea of diffusion models was to define a noising process that adds noise to the data, transforming the data distribution into a noise distribution. And here we can now ask a different question. Namely, given a noisy sample, how can we move it toward the data? And this is much simpler to answer. So for instance, we can define the velocity field, which for a given noisy sample is just the average interpolation, the average difference between noise and data samples that intersect at xt. And we can train a model for this. So we just take a data sample from our data set, we take a noisy sample, we interpolate them, we feed it to the model, and then the model predicts the difference between noise and data. And then once we have this model, we can generate new data by taking a noise sample from our prior distribution and then just moving it along the velocity field. So iteratively applying the velocity field. Now, this is principled. So if we have enough data, enough model capacity, then the minimizer of this training objective will provably generate a data distribution. And this is simple, right? We just take a noisy sample, feed it to a model, and predict something. This is just supervised regression. It's the simplest supervised learning problem there is. And this is why these models scale so well. Now let's take a step back and think about what we actually want to generate. Or speaking mathematically, how do we specify this distribution for which we want to learn a model? And there are really two natural ways of doing this. One is from examples. We take a data set of examples and then learn a model to match the data distribution. And the other way is from outcomes. We have a model, we generate some outcome, we score the outcome, and then we update the model to maximize the score. This is very natural. Like we humans, we're done like this. We try to imitate others, but then we try our own. We learn from our own outcomes. And most frontier systems these days are a combination of the two approaches. In language models, we first train them on all available data there is. And then in order to improve them, for instance, for mathematical reasoning or for coding capabilities, we give the model some challenging task, we let it produce some output, and then we just verify if the output is correct or not, and use this to update the model. Now, why is that? Because it's much simpler to just verify an output than to come up with good examples. So it's much easier to check if a mathematical proof is correct rather than coming up with a proof. A good example is also robotics. If we want to train a robot just from imitation data, we would first need a person to control the robot, then we can record this, and then train a generative model on the recordings. But in order to be very effective, to let the robot solve it efficiently, it needs to learn from its own outcome. Right? So we have now diffusion models on the one hand, this dominant class of generative models, and we have reinforcement learning as the learning paradigm on the other hand. Now, diffusion models have been developed to train from examples. They're well understood in this regime and very scalable. Training diffusion models with reinforcement learning is not so well developed yet. Existing approaches, they're either very complex, they scale poorly, or they are inefficient. So this is what we wanted to develop here. An approach to train diffusion models with reinforcement learning that, like pre-training, is principled, it's simple, and thus scales. So formally, this is the problem that we consider. We are given a pre-trained diffusion model. This can, for instance, be a text-to-image generation model. So you can prompt this model. You can say, give me an image of a red zebra. And this is what the model gives you. Like, this is the actual output of Stable Diffusion tree. It's a zebra, but it's not red, because the model hasn't seen a red zebra in the training data. And then we have a reward function. The reward can also, in this example, be a vision model that takes the output and takes the prompt, and then verifies if the output matches the prompt. And now what we want to have, we want to find a model for a distribution that maximizes the expected reward, but still generates realistic-looking images. So it stays close to the pre-trained model in a KL sense. And the optimal solution for this is this exponentially tilted distribution, which is proportional to the distribution of the pre-trained model times the exponential of the reward. And in this example, it would be a text-to-image model that when you ask it to produce an image of a red zebra, it actually gives you such an image. Now, the idea of getting such a model is the same idea that we use when we develop diffusion models in the first place. We define a noising process starting from these endpoint distributions, from the reference distribution of the pre-trained model and from this optimal distribution. Of course, we cannot explicitly construct this, like at least the blue one, the optimal one, because we don't have access to this endpoint yet, but mathematically we can write it down. And then we can think about these velocity fields, the reference velocity field, which is just the pre-trained model, and then the optimal velocity field corresponding to this optimal tilted process, which is the model we would want. And here's an insight from stochastic optimal control theory, namely that the two are related. So specifically for a noisy sample xt, the difference between the reference velocity field and the optimal velocity field is proportional to the gradient of this expectation here. Now, with a bit of algebraic rewriting, one can show that this expectation is well approximated by this other expectation here. And this now is really just a residual. It's the difference between the pre-training target and the optimal velocity field multiplied with a reward. And now this is something we can estimate on policy from the current model, and we can use this equality to obtain a consistency loss. So specifically, we do the following. We take the current model, starting from the pre-trained model, we sample from it, we get a sample, we evaluate the sample, and then we do the same thing as we do in pre-training. We just add noise to the sample, and then we regress again towards an analytical target, which we construct using the noise vector, the sample, and the reward. Now, if you think about this in terms of computational cost, step 1 and step 2 are expensive. Step 3 is very cheap. Step 3 is just regression. It's the same thing we do in pre-training. But here a key insight. We can use the same endpoint and the same reward to obtain multiple regression targets. So we can just add different noise vectors to this sample. And thus we can amortize the cost of sampling and reward evaluation. And we will then end up with an approach that is almost as efficient as pre-training. Now here are some results of what this gives you. You can take the same pre-trained model, this is Stable Diffusion. When you ask this model to generate an image with some text, it will generate something, but it's not really legible text. So for instance, this is an example where we ask the model to generate a globe with the equator line marked. And now we can use a reward model, which is an optical character recognition model that just checks if the image actually contains the text that we asked it to. And then if we use this reward to improve the model, after a few, actually like just 70 steps, we get a model that perfectly renders text. We can also take a human preference model that has been trained to predict how much, like if an image is preferred or liked by humans. And so if we take the base model and we ask it to generate some image, so for instance, an image of a wooden Ferrari, this is what we get. It's a quite ugly looking Ferrari. Maybe not as ugly as the new Ferrari Lucia, but But if we then improve the model with our human preference model, we get a very nice looking Ferrari. And this is all at a fraction of the cost of prior methods. This is another example. So we have a diffusion model that generates control signals of a robot. Here the robot needs to place cubes at some designated places. We only have little training data, so the robot performs quite poorly. But if you actually look at the image, you get quite nervous. And then if we improve the model, so the reward here is just, we have a positive reward if the robot solves the task. And then if we improve it with our method, it solves the problem very quickly. Okay, that's all from my side. Thanks for the attention.
Thanks a lot. We have time for at least one question. There's one.
Yeah, thank you for the interesting talk. For reinforcement learning, the problem is always the measuring of the quality, and I didn't quite get exactly how you do that in the diffusion process. You were talking about human preference model at the end, and in between you said something about vision language model scoring something, but how exactly do you get the good or bad measurement?
So you have a pre-trained model, and the pre-trained model generates something, okay? And then you have a reward function, and this reward function gives you a score for the generation. So for instance, you have like a pre-trained model, and okay, ignore these slides. It generates something, and then the reward tells you if this generation is good or bad. And now we want to steer the model so that it always produces something that is good.
Yeah, but where does the reward come from? How do you get this model that knows that this is a good result?
Yeah, this is like a separate model. So it can be, like the human preference model has, for instance, been pre-trained on, it has been shown examples of images that are preferred by humans and not preferred. So it's a separate model. So for instance, in the optical character recognition setting, you have like an optical character recognition model that checks the image if there is some legible text, and then it gives you a score. Or in this robotic example, you can write, the output is the control of the robot, and then the reward function is simply 1 if the task is solved and 0 otherwise.
But isn't that horribly slow? If you apply the OCR model to the result of the image, then it takes ages. How do you scale that for training?
Right, yeah, that's a good point. So that's what I wanted to say here. So sampling from the model is slow, and then evaluating the reward can also be very slow. But the good thing is that once we have a sample and a reward, we can construct a lot of training samples, because training means we add noise to the data and then we predict something. And we can just add different noise vectors to the same sample, and so we don't need to re-evaluate and resample every training pair that we use.
Thank you.
Thanks a lot.
Other questions? Maybe like one very quick one would still fit in, if there is one. Yeah, there's one.
Just real quick, in a lot of diffusion model talks, people forget about the conditioning. Can you comment real quick how you condition on the text prompt? Do you just do stable diffusion as is, or do you do things?
Yeah, it's the normal diffusion model. Like it can be conditional or unconditional. It doesn't really matter.
Okay, good.
Yeah.
Perfect. Then let's thank Andreas again.
Thanks a lot.